This is the last lecture that's developing our three-dimensional crystallographic point groups and, well, with just rotations, without adding any what we're going to call later extenders. The extenders being things we know about like mirror planes, but also some new things like the inversion centers. And so, just these point groups based on rotation, that's what we're calling it, axial point groups. It's not a complete set yet because we haven't added any of the extenders, but just working with rotations, hence the term axial combination point groups. We have arrived at the 11 combinations, which we'll show you at the end of this lecture. We'll cover first the last sequence that's based on our cosine A, cosine B, cosine C expressions that we had derived. And in this case, remember the other one was still on the diagonal if you had an AB matrix like we drew a few lectures ago because it was 3, 3. This is the one that appears actually that is not on that axis because A and B are different. In this case, one of them is a twofold axis, the other one's threefold axis, and then that shows us that that the C must be a fourfold axis. And so we're showing you that here, cutting right to the chase. If we call alpha the first one and beta the second one and C the last one like we've been doing, alpha equals 120 degrees. Oh, I'm sorry, I actually did that the other way around. This is alpha, this is beta, this is say, it doesn't matter. But so alpha is 120 degrees, right? Beta is a rotation of 180 degrees, and then gamma is rotation of 90 degrees. And again, if you go and plug in those rotations into cosine and cosine, you see that it works, and there's finite angles. That is the angle between remember that in we had our the angle between B and A is C. The angle between C and A is B, and the angle between B and C is A. So the angle between B and C, which is the 180 degree, and the fourfold axis would be 90 degrees. You can see that here. We drew that in. This is 90 degrees. So that makes sense again if we choose the cube, because this has a fourfold axis and is popping out the top, and this guy's 90 degrees away and coming out here. If we look at B, which is the angle, recall, between C and A, so that's this one here. We've already covered this because this is a normal to the 1, 1 plane, so this is going to be our 55 degrees again, the angle between a 1, 1, 1 plane and a normal to a cube face, right? And C is going to be half of 70.53, which is 35.26. Now that's the angle between A and B. And the reason I put it that way is that if I were to draw this continuing down here, that's the same one. But if I were to look at the if we were to look out this way, and we were to see that coming out directly this way is another twofold axis, for example, then remember in the last lecture we had shown that the angle between 111 directions is 70 degrees. And if you just look by inspection here, if this one coming in the upward corner is 111 direction and the one going out the bottom corner is another one direction, that angle is 70 degrees. And halfway as we rotate down, we're going to be going through a twofold axis. And so now, just by inspection, you can show that the angle between the nearest 111 and a twofold axis is 35 degrees, right? So again, with the cube, you can kind of show that this solution that we got from our cosine A, cosine B, cosine C expressions kind of points right to a cube because these are classic angles for that. So if we look at the stereographic projection for that, we have to have that fourfold axis coming out the top, and we have a fourfold axis coming out of each side. And right away you can say, if I forgot to make a correction here, there's a fold axis, of course, coming out straight at you. So this should be a nice black square. You can tell we copied this over from 2.3 and modified it in order to make this one so we don't have to redraw everything. And then coming out of the every edge of the cube, this is, for example, this one coming out of here is this one here, right? One on the other side, one on the top edge, right? Then one on the bottom edge. So again, just to orient yourself, this would be looking down at the cube, a sphere coming out of a cube like this. So recall that we'd have, two folds here, which are this one here is this one here. If you're just looking at the square part, right, we got this one in the middle. Then coming out of the corners, we have the threefold axes, which is why we have this one, this one, this one, this one. So again, coming out of the stereographic projection, and then the twofold axes going through the side, but showing up on the other edges. So for example, if you're confused about this one, if I was looking down here with my eye, right, that would be this one, and this one over here would be this one, right? In other words, the like these guys, the ones coming out of the edge, right? And the way you can see that, of course, is that there's a fourfold axis on the right, so there's going to be a fourfold axis here coming out, and coming out of this edge, there's a twofold axis. So as you go from top and just rotate around on the great circle that's perpendicular to your eye, right, you would see fourfold axis, twofold axis, fourfold axis, which is why we get that kind of stereographic projection. And that is 432. So having covered 432, let's now quickly summarize. At the top here, you can see that we have the ones with only a single rotation and no other rotations. Those are the simple single complex axes, single axes with no other rotations, right? So that's the simplest axial combination where there's only one axis, right? Then we said, all right, we're going to derive our little equation, and we found out that the N22 set is very rich and has a lot of solutions. And these were all the N22 ones that we did, right? And again, instead of having you crank through the entire different combinations of rotations about A, B, and C and see which one's the cosine A, cosine B, cosine C equation solved, we kind of told you ahead of time. Then finally, again, in the same spirit, we said, by the way, there's one solution that's out by n33 and it's 233. And in fact, this doesn't generate a new threefold axis. And so there you go. And then finally, the one that's really kind of used to our cubic structures. If you use the cubic structure, this is the cubic symmetry one, which is 432, where there's a fourfold axis working in harmony with the threefold axis coming out of the corner with twofold axes coming out of the edges. And those are the 11 crystallographic axial combination point groups where we have not added any extenders. Now you can imagine in our work going forward the kinds of extenders that we might be able to. We're going to have the mirror operation, right? That's certainly for a point group that can operate about a point. And now we have our inversion operator, right? So this is represented. The thing was M. We draw a line. And then this thing here will be like a little tiny circle. And those are things we can do about a point. We're not going to add translation yet because recall that makes the lattice, and that is something that we need to do also. And then after we add extenders to our point groups, after we create the lattices compatible with all that, we put them together, we end up with the total number of combinations for the crystallographic 3D space groups, right? But again, we're still on point groups, haven't added, we're going to call these things the next lecture extenders, because they'll take our axial point groups and they'll basically, wherever we can add them to generate more different kinds of point groups, we will. And it'll, of course, will multiply the number of point groups that we have when we add these extenders.